This lesson is an introduction to thermal physics and covers the topics of temperature, heat, and internal energy. Here are your objectives. So first, let's imagine placing two objects in contact with each other. One object is hot, and the other object is cold. And we know from experience that the cold object will start to warm up, and that's because energy is being transferred from the hot object to the cold object, and it will only ever be transferred in that direction. Now, when objects of these different temperatures, one hot and one cold, are placed in thermal contact, that's what we've done here. It means that they're in contact so that energy can be transferred. Energy will continue to transfer between them until they're both at the same temperature. And when that happens, when they're both at the same temperature, we say they have reached thermal equilibrium. And we call the energy that is transferred in this way as a result of temperature difference, we call that energy heat. So this energy here that's being transferred, we're going to call heat. Heat then is given the symbol Q, and because it's energy, it's in units of joules. And as we'll also see in a later lesson, energy can be given units of calories, which is abbreviated CAL as well. Now, we've already seen another kind of transfer of energy. I've just said that heat is a transfer of energy that occurs as a result of a difference of temperature, but we've also seen that work is a transfer of energy as well. When you exert a force through a distance, you're transferring energy, you're doing work. But work is more macroscopic, larger scale, and it's more mechanical. We can see an object that's moved through a distance by a force. In contrast, heat is non-mechanical and it's microscopic. We don't actually see the interactions between the moving particles in the objects that's transferring heat, but they are there. So although we can't see them, the molecules in the hot object up here are jiggling back and forth, and they are transferring that kinetic energy to the neighboring molecules of the cold object, and they're starting those to jiggle back and forth. So there still is a force being exerted through a distance, but it's on a microscopic level. So both heat and work transfer energy to an object. Again, heat is non-mechanical and microscopic. When we study thermodynamics, we will look at the interactions between these two much more closely. Now, as we've said, the spontaneous transfer of heat always goes from hotter objects to colder objects. It will never go the opposite way spontaneously. If we want to transfer energy from colder objects to hotter objects, like we do in a refrigerator, we have to do work. We have to put in energy. So we've defined heat as the energy that's transferred from a hot object to a cold object as a result of that difference in temperature. Now let's define temperature more carefully. Temperature is a measure of the average translational kinetic energy. The average translational kinetic energy of the molecules in a substance. We saw above when I drew the two objects, the hot and the cold object, we said that the energy was being transferred as a result of the jiggling back and forth of the individual molecules of the hot object bumping into the ones from the neighboring cold object. Temperature, again, is a measure of the average translational kinetic energy, this energy of bumping around of the molecules in a substance. We specify translational because when we get more complicated molecules, like those with two atoms in them, there can also be vibrational kinetic energy and also rotational. So temperature is a measure of the average translational kinetic energy. Also, it's the average. In a given substance, some molecules or some atoms are going to have more kinetic energy and some are going to have less. They're in a distribution from less to more, but this is the average that we're interested in, and temperature is a measure of that average. In physics, we're going to use two different scales. We won't use the Fahrenheit scale, but we'll use the Celsius scale or the centigrade scale that you're familiar with, as well as the Kelvin scale, also called the absolute temperature scale. And the temperature in Kelvin is found from the temperature in degrees Celsius with 273 or 273.15 added to it. That gives us the temperature in Kelvin. So 0 degrees Celsius is roughly 273 or 273.15 degrees Kelvin. 20 degrees Celsius would give us 293 Kelvin, and 100 degrees Celsius is 373 Kelvin. So there's just a little bit of practice. Now, 0 Kelvin, or negative 273 degrees Celsius, is also called absolute zero, and it's the coldest temperature theoretically possible. And actually, at that temperature, all of this molecular motion would stop. Okay, we've defined heat, we've defined temperature, now let's define internal energy. Internal energy is the sum of all of the energy in the molecules in an object. So it doesn't include the overall center of mass potential energy and center of mass kinetic energy. So let's say you had a box that was flying through the air. It's above the ground, it's got potential energy, it's got kinetic energy. Those are not the energies we're interested in. We're interested in looking inside of it, that's why it's internal, and looking at the kinetic and potential energy of the molecules in the object. So the internal energy is made up of the molecular potential energy and the molecular kinetic energy. And we've already seen that temperature is a measure of the average translational kinetic energy. The potential energy is related to intermolecular forces and bonding. When you add energy to an object by heating it, transferring heat to it, you can either increase the molecular kinetic energy, which is reflected by an increase in temperature if that's increasing. If the average kinetic energy is increasing, or the average translational kinetic energy is increasing, the temperature will increase. You can also increase its molecular potential energy, and that's associated with its phase, whether it's a solid, a liquid, or a gas. And the energy that you add can go into one or the other, or both. When you change the phase of a substance, when it goes from liquid to gas or from solid to liquid, what's happening there is that the molecular potential energy is changing, but not the kinetic, and we'll explore that more in a future lesson. So that's an introduction to thermal physics with a definition of temperature, heat, and internal energy.